Okay, so we are in the middle of constructing the spectral sequence, and it's a big machinery. So it takes a few days. So last time we looked at a filter complex with a filtration of finite length, and we showed that eventually the spectral sequence of the filter complex stabilizes, right? And E infinity computes the associated gradient complex of the cohomology of the filter complex. Okay. Now, today we want to look at the situation of an infinite filtration. Yeah. So this is the picture. So this part is K. And we have a filtration. We extend the filtration to negative degrees. Okay, so this part is K minus 1. K minus 1 is the same as K0. Okay, K0 is K. And then K1 is a subgroup. And then K2 is a subgroup. Okay. And this could go on forever. Okay. Yeah. So let K be a filter by K minus 1, which is K, which is K0, containing K1, K2, and so on. And we have an inclusion from KP, KP plus 1 into KP that we call I0. And then there's a quotient KP over KP plus 1. Okay. For each P, you have a short exact sequence, and then we can take the direct sum over all P in Z. Yeah. Okay. And this complex we call C. This is the same thing. C, and the quotient we call B. Okay. And this short exact sequence gives rise to a long exact sequence that we write as a triangle. So H of C maps to H of C, which maps to H of B. Okay. Okay. So this is an exact couple, and we call it A1, A1, E1. And then, you know, you can take derived couples. So the derived couple would be IA1 going to IA1 going to H of E1. Okay. So that's the first derived couple. and this we call, oh, so then this we just call A2, A2, and E2. Okay? And in this way, we get our spectral sequence. Okay. Okay, so, it might be that the filtration goes forever. However, it could be that this complex K is graded. And it might happen that in each degree, the filtration is finite. So the picture might look like this. Okay. Yeah, so K might be a double complex, right? And so degree N would be these boxes. And the filtration is infinite. But you see that if you just look at elements of degree N, then the filtration is finite. Okay. So even though the filtration goes on forever, degree N consists of these diagonal elements. And so after, like N steps, then the filtration becomes 0. Okay, so you can have a situation like this. And then in this case, we'll show that in degree N, the spectral sequence will stabilize and it will again compute the associated gradient complex of the cohomology of K, but only in degree N. Okay, so yeah, so let's see. Let me state the theorem. Theorem. So let K, which is graded, be a differential complex which is filtered by an infinite filtration suppose in each degree N, you have a filtration just on degree N. So with KNP, the degree N elements intersected with the filtration KP. Suppose in each degree, this filtration in degree N is finite. The filtration, so Kn, which is Kn0, and it contains Kn1, okay, contains Kn2, but in degree N, it terminates. So KNL, okay? Now this L depends on N because in degree in different degrees, you can terminate at different points. So I put Ln there. So in each degree, the filtration is finite. Of length Ln. Okay, then the spectral sequence ER in degree n stabilizes. Okay, that means it becomes constant after a while. And so you have a E infinity in degree n. And that is the associated Grady complex of the cohomology in degree n. And when you take the associated Grady complex, it's always respect to a filtration. So with filtration, FPN, so FPN is just the elements of degree n intersected with FP. Okay? FP is the filtration on the induced filtration on the cohomology, where FP is the induced filtration on H of K that we defined last time, right? Yeah. And in this situation, like for example, if you have a double complex, okay, then the filtration will always have finite length in each degree. And in this way, you can compute the cohomology, degree by degree. Yeah. All right. So let's try to prove this theorem. Yeah. Okay, so we'll just follow the proof that we had last time. What we want to show is that these A's will stabilize in each degree, okay? And then the I's become inclusions. But there's a difference, right? Because, you cannot just look at degree n of an exact couple, because that doesn't make sense, because this K is the connecting homomorphism. So K increases the degree by 1. Okay, so yeah, so there's something in the argument last time that won't work when you just look at degree n, okay? Because in degree n, you don't have an exact couple. Okay, so let's see how to fix that. Uh-huh. Okay, yeah. Uh, okay. All right, so we want to look at A1 in degree n. Start with that. Um, okay, so let ARN be 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 the elements of AR of degree n. Yeah, because A1 has A1 is the cohomology of C, you know, so every element has a degree, and um, A2 is IA1 is a subgroup of A1. So, you know, every element has a degree. So you can look at elements of AR of degree n. Um, okay, then A1n, it's elements of H of C of degree n. So it's Hn of C. And C is the direct sum of K P plus 1 over all P. Uh, but you know, that's the same as the direct sum of Kp over all P. Um, however, yeah, we said that in degree n, you know, it terminates after a finite number of steps. Okay, so so this actually is not a sum over all integers. Um, yeah, what is it a sum over? I mean, because after a while, all the terms will be 0. So actually, this only goes up to KNL1. P less than or equal to L1, KP. Okay? And then A2, um, so that's a subgroup of A1. So, oh yeah, yeah. So now let me write this out. So this is going to be when P is negative. So you, let me see, just a minute. Hn of say K minus 1. Okay, that's the same as Hn of K. That's the same as Hn of K0. And so, so the next term is Hn of K1, and then Hn of K2. Okay. The last one is Hn of KL1. And this goes on forever. Okay, so A1n is the direct sum of all the terms here in this sequence. Um, and then you take I, right? So, yeah, these maps are all called I's. Okay, so these maps are induced by inclusions, but they are not inclusions. However, I of HK1, okay, that's in here. The image of this is in here. Now to get A2, you just take I of everything in A1. So you have I, H, N, K2, and that's in there. And then no, just a bit, just I of H, N, K3, and that's in there. Let's see, and then here, okay, I of this, well, but this is already everything, okay? When you take I, then it's the same thing. Okay, and then you have a map here. Okay, and this goes on forever, okay? Okay, now this is a commutative diagram because I in A2 is just the restriction of I in A1, okay? So this is a commutative diagram. And when you look at this map I, you see that, let me see. So this map I, it goes this way. No, just a minute. No, this map. Look at this map I. Okay. So this map going this way is the same as going this way. So this map is actually an inclusion. Okay, because going this way is an inclusion. Okay? Yeah. So you see that the first map becomes an inclusion. This one is an inclusion. So A2 N is the direct sum of all of these terms, but the first map becomes an inclusion. That's just like what we did last time. And so if you look at A3, then the next map will become an inclusion. Okay? Yeah. So, okay, so far it's the same argument as last time, that after finitely many steps, I guess after L1 steps, then all the maps become inclusions. Okay? So, so yeah. So for this is like last time. Because in each degree you have a finite filtration. So after L sub, just a minute, how many? um, hmm. And this seems to say that because I start with KL1, oh, I'm sorry, this is not KL1. What should this be? Huh? Ln, yeah, because we're in degree n, right? So in degree n, um, yeah. In degree n, the filtration has length Ln, so this should be Ln, right? In degree n. Yeah, yeah. So this should be Ln. Yeah. In degree n, we assume that the filtration has length Ln. Okay, so this should be degree Ln. Yeah, and so after Ln steps, all the maps become inclusions. So A N R is the direct sum of uh, H n of k, say -1, and that's the same as Hn of k0, and yeah, Hn of k0, and then degree 2, you would have okay, this is yeah, this is the same as Hn of k1. So this is IHN of k1, IHN of k1, and then, okay, so in A3, you'll take I again, so you'll get I square. I square HN of K2, I cube HN of K3, and the last one is ILN HN of KLN. Okay? So all the I's become inclusions. This goes on forever. Um, and yeah, and then here, so let me see, what is this? So yeah, so we're gonna call, let me see, so this is actually Hn of K, and so this will be, this, so you get a filtration, and this we will call Hn1, and this is Hn2, this is Hn3. You get a filtration in degree n, HNLN. Okay? Yeah. So where this filtration, HNT, you see that it's I to the P HN of KP. Okay? So it's really the degree n elements of the induced filtration. Huh? Yeah. Yes. Okay. So that's That's A and R. And now let's look at ENR, the spectral sequence. Okay, so we have ANR, and then it goes to ANR, and this is IR. Okay, but this has become an inclusion, and then you map to ERN. Okay, but you see, you don't have a map this way. If you don't look at degree n, okay, then you have an exact couple. You have an exact triangle. But in degree n, there's no map this way. Why is that? So in degree 1, let me see. So no, just a minute. If R is 1, A1 is just H. It's just the cohomology, right? A1. We started with this. So this is our E1. This is A1. Okay. When R is 1, you know, you have this, well, without the n, you have an exact triangle, but when you have an n, this you have a map here, but it doesn't go to Hn of C, right? Where does it go? I mean, where does this triangle come from? Yeah, I mean, the triangle comes from the short exact sequence. It's a long exact sequence of the short exact sequence. And so this is the connecting homomorphism, you know, so it should actually go to Hn plus 1. So you don't have a exact triangle like this in degree n because this map K raises the degree by 1, okay? So we don't have an exact triangle in degree n. Yeah. In degree n. I mean, KR is actually K. It comes from K, right? Each time, you know, like K2 was defined to be K1 and so on. So in degree n, there is no exact triangle. Okay, so because K raises the degree by 1. Okay. So this is where the proof is different from last time. Last time, you know, you did not restrict to a single degree, so you get an exact triangle. well, even though you don't have an exact triangle, I mean, you have an exact sequence. So, but, you know, but we have an exact sequence. Okay. So AR N, okay, it still goes to A N R, and that goes to E N R, okay? But E N R raises the degree by 1, so it goes to AN plus 1 R. And then that goes to AN plus 1 R. And this will come from E n minus 1 R, okay? Yeah. So instead of an exact triangle, you have an exact sequence. And then this map is I. This is I. And this map is this map, KR. Okay. Yeah, KR. Okay. This is really IR, but IR is I, right? So, but we know that I is an inclusion. So, since I is an inclusion, and the sequence is exact, so the image of KR is the kernel of I, and the kernel of I is 0. So what does that say about KR? It's a 0 map. So KR is a 0 map. And that means you can start with 0 here. Yeah. So yeah. So we get an exact sequence. We start with 0, and then we have ANR, I, ANR, and then it goes to ENR, and then it goes to 0. Okay? Yeah. Now, ANR, right, for R large, it stabilizes. So we can say for R greater than Ln, it stabilizes, and we call that AN infinity. Okay. Yeah. And let me see. So what is ANR? Okay. I had erased it, but remember there was a sequence of inclusions. So ANR is actually the direct sum of these filtration H and P plus 1, right? For all P, it was, well, you can say P in Z also, okay? It's just that when P is large, it's all 0. And this was the direct sum of the same thing, but you sum over P, okay, for all P in Z. And this is the quotient. So it is the direct sum of F and P, over the direct sum of F and P plus 1. This map I maps FP plus 1 to FP. And this, by a theorem of algebra, this is the direct sum of H and P over F and P plus 1. Okay. However, you know that for P negative, they're all the same. For P negative, it's everything. It's just H and a K. So in fact, this starts at P equal to 0. Okay? And then for P greater than Ln, it's all 0. So this ends at Ln. And you have Fp n over F n P plus 1. Okay, when you have a filtration and you take the successive quotients and then sum that up, what is this called? This is the associated gradient complex of the filtration on Hn of K. Okay? And it's with respect to the filtration Hn of K, which is F0 and then F1n and so on. Okay. Yeah. Yeah, so because the A's stabilizes, so does the E, right? Yeah, so that value we call E infinity. So let E n infinity be E n R for R greater than Ln. Yeah. So then En infinity, that's this, is the associated gradient complex of H and K. Yes, and that's what we wanted to prove. Okay? Yeah. Yeah, so if in each degree n, the filtration is finite, then you can still compute the cohomology in degree n using the spectral sequence. Okay. Okay, so let's stop here and take a break for 10 minutes, and then we will apply this to a double complex and see what we get. Now, I will be in my office, maybe like, let's say after 4 o'clock today. So if you have questions about the homework, which is now due next Monday, you can come to my office and I can help you with the homework. Okay. Yeah. So today at 4 and after. Okay. Now we want to apply what we just did to a double complex. Okay. So, and we want to work out these differentials, D1, D2, D3, so that, we know what we are getting, okay? And we also want to relate the spectral sequence of a double complex to what we did earlier, when we talked about the tic-tac-toe lemma, H little d, H delta, HD, and so on. Okay. Okay, so now we have a double complex with 2 degrees and 2 differentials. K is the direct sum of KPQ, and we're going to assume that it's a first quadrant double complex. So, so PQ, they're in Z, but we assume that KPQ is 0 for P negative or Q negative. Okay. So it's a first quadrant double complex. And we're going to filter by P. Okay. So let KP be all the, let me see, so K1 would be when P is greater than or equal to 1, right? So KP would be all the KPQ such that P is greater than, oh no, God, I can't use the same P. KP would be KIQ, where I is greater than or equal to P. And Q is in Z, but it's really, just let's say Q is in Z, okay? Yeah, so this is a filtration. And okay, so let's start with the first exact couple. Oh yeah, so this situation satisfies the hypothesis, of the theorem we just proved, right? In degree n, the filtration is finite. Sorry about this. Okay, and we start with the first exact couple. which is HC. Oh yeah, so let's just review again. What is C? So C, yeah, so we have the direct sum of Kp over Kp plus 1. No, the direct sum of Kp plus 1 into the direct sum of Kp into the direct sum of the quotient. And this is C, this is C, this is B. Okay. And the first exact couple is this one. Okay. So this is A1. This is E1. I, J, K. So E1 is the cohomology of B. But what is the differential on B? Yeah. So let's work out the differential on B. Yes. Now, the differential on B is induced from the differential on the entire complex. Let me see, put this up there. Okay, because a filtration is a sequence of subcomplexes, so D will take Kp to Kp. And because Kp plus 1 is also a subcomplex, this D, it takes Kp plus 1 to Kp plus 1. Therefore, it induces a map on the quotient. It induces D on the quotient. And if you take the direct sum, okay, then that's B. Okay, so B, so the differential on B is really this big D. Okay. Okay, now let's write out the formula. Okay, so so let's say you have an element B in B. So let B be in B, but B is a quotient, so it's really a cohomology class. Yeah. So with B in KP. Mm. And let's say it has degree n, okay? Okay. Okay. Now, what is big D? Do you remember the formula for big D? The formula for big D, when you have a double complex, it has a horizontal part and a vertical part. Hmm? Yeah, D prime plus D double prime. So D prime is the horizontal part, and that's just delta, the alternating difference. And then D double prime, the vertical part, is minus 1 to the P of little d. Okay? And so let's apply it to B. Let me see. Yeah, so we apply it to B. So it's this applied to B. And so it is delta B plus minus 1 to the P D. Okay? And then we take the quotient, take the equivalence class in the quotient. Well, but you see, where is this? Delta B. So delta B is here. dB is up there. So delta B has one extra P, right? It's now B is in KMP, but delta B is in K M plus 1, P plus 1. Okay, the degree increased by 1, and it's the P degree that increases by 1. Okay, but when you take the quotient, yeah, what happens to it? You know, you take the equivalence class in the quotient, then can you tell me what happens to this delta B? It becomes 0, yeah? Because it is in Kp plus 1. Okay? So when you take the quotient, this is actually just minus 1 to the P of dB. Okay? And this is minus 1 to the P of D of the class of B, because that's how we define the, an operator on the quotient. We just define it to the class of dB, okay? So what this says is that big D, the differential on B is just minus 1 to the P little d. Thus, D on B is minus 1 to the P D. Okay? And okay. And so this cohomology, I mean, this is H big D of B. Okay? So E1 is HD of B, and that is really just the same as H little d of B is Kp over Kp plus 1. How would you picture this quotient, Kp over Kp plus 1, here in this double complex? What is Kp over Kp plus 1? It is just the pth column, right? So K1 over K2 is just this column. Okay? So when you take the direct sum over all P, you just get all the columns. And so that is really just K, right? You get all the boxes in K because you get all the columns. So this is HD of K. Okay? This D goes up. Yeah. So that is what E1 is. E1 is H little d of K. Okay, now let's work out E2. Okay, so E2 is yeah. So now this is A1. So now you have A2 to A2 to E2, and E2 is the homology of E1. You know, with respect to D1, and D1 is K composed with J. Okay, and we know what J is, right? J is just a projection. So yeah, so J, okay, of a cohomology class C, by definition, it's just the cohomology of the projection. This one, this is I0, this is J0, okay, and so you just project down C, and then you take its homology class, okay? This was the definition of J. And K, well, K is the connecting homomorphism in the long exact sequence, okay? So that's what we need to work out. What is the formula for K? So K from H of B to H of C is the connecting homomorphism in the long exact sequence, and B is this, C is this. And you remember how we got the connecting homomorphism, right? Can you do a gesture that show me how you get the connecting homomorphism with your hand? Right, yeah, you do this, right? That's how you get the connecting homomorphism. So you have Kp plus 1 going into Kp. That's actually an inclusion. And then, no, this is degree n plus 1. And that comes from degree n. Uh, right. So, yeah, it comes from big D, right? The differential on the case. And this projects down to the quotient. Yeah. So if you start with a class here, now so that comes from B here, and then you go up to dB. Okay, and this dB will be in here. Yeah, that's right, because the degree increases by 1, and you know that the P degree also increases by 1. Okay, yeah. So in fact, K is just big D. So K of the class of B, okay, yeah, this is, it is the, oh, just now I'm a little bit afraid to write the class of big D because the class of big D is 0, right? Okay, K of a representative. Yeah, K of a representative should be big D of K. And okay, and big D of K is big D of K is delta plus minus 1 to the P of D. Oh, yeah. Okay, so no, let me see. Yeah, what do we know about this B? Yeah, so let's see, what did we just conclude? Yeah, so yeah, we just concluded that, oh gosh, I erased it here, but I can still see it faintly, that E1 is HD of B, and that's HD of this quotient, and that's H little d of B. So, so an element of E1 is a cohomology class in H little d of K. And to be a cohomology class here, dB has to be 0, right? It has to be a cocycle, right? Yeah. Okay, so now we start with an element B. Yes, we want to figure out what this K is. So we start with an element B such that dB is 0. Okay. So let B be in E1, which is H little d of K. And so you know that dB is 0. Okay. And therefore, okay, KB is big dB and is this, but dB is 0. So this is delta B. Thus, so because dB is 0. And then D1 of the class of B, you know, that is JK of the class of B, but KB is delta B. So that is just J of delta B. And J, right, J is just a projection. You know, so right here, J is just the class of the projection. Okay. So yeah, so when you project, I mean, you still get the same class. It's this, right? Yeah. And so this is the same. This is how we define delta on a class, right? We define it to be the class of delta. Okay. So what we have shown is that D1 is delta. Thus, okay, thus, D1 on E1, which is H of B, which is HD of K, is delta. And so therefore, E2, which is the homology of E1 with respect to D1, it is H delta of E1, and E1 is HD of K, so this is H delta HD of K. Okay. So you see that the spectral sequence of a double complex actually starts with HD and then H delta HD. And that's what we had before.